Good morning. Now that we have derived helicopter 3 degrees of freedom model, let's try to trim the helicopter for forward flight. I will learn you to trim the helicopter and represent the trim curves. If you recall, the dynamic equations of motion in a longitudinal model are derived as a function of the surge velocity, u, of the heave velocity, W, and the pitch moment, Q, and the fuselage attitude. Now, how to solve the helicopter trim? In fact, in forward flight, you can say that the thrust equals with the resultant of the vector formed by the weight and the drag of the fuselage. We will demonstrate this relation, and for that we will recall the forces and moments in the 3 degrees of freedom that need to be zero. We know that the trim of a helicopter means that all the acceleration, so the u dot, v dot and q dot, have to be zero. Now, performing this, we obtain first, the pitch moment mi equals with 0 is equivalent with actually theta c equals with a1. That means that the longitudinal cyclic equals with the longitudinal disk tilt angle. In trim, in fact, the tip-off plane coincides with the shaft plane. Therefore, it is parallel to the body axis x. Now, if we now take the moments, the forces around the x-axis, substituting theta c equals with a1 gives us 0 in this relation, and recalling that the pitch of the fuselage is actually also the u divided by w, we obtain that the tangent of pitch angle equals with minus drag of the fuselage divided by the weight of the helicopter. In trim, the pitch angle is negative. So actually in forward flight, the fuselage is nose down. Finally, if we take the Fz forces and substitute the previous obtained relations, we obtain that the thrust equals with the square root of weight squared plus drag of the fuselage squared. So indeed, this is the case of a trim in a longitudinal model. Now, some examples of relations that we will need. We learned that longitudinal cyclic equals with a flapping angle. Recalling the angle of attack of the rotor in the control plane as alpha c equals with the theta c minus the arctan of w over u, it follows that the angle of attack with respect to the control plane equals with the angle of attack with respect of the disk plane plus the longitudinal cyclic pitch. How to find the trim solution? So we will start from the thrust coefficient expressed in the Glauert theory. We demonstrated that this is relation that gives us the thrust using the Glauert theory. But for our trimmed helicopter, we know that the angle of attack of the disk plane equals with the alpha c minus a1, and looking at relation 9, we see that this is the drag of the fuselage divided by the weight of the helicopter. Also, we know that the thrust equals with weight plus the drag of the fuselage squared and squared of. Therefore, substituting these two relations into 10, we will obtain an equation with one unknown, which is the lambda e, which is the inflow ratio. Solving this relation for our trim, it will give us the induced velocity for that trim condition. Further, We recall the thrust coefficient in the blade element theory. And recalling that the ratio lambda c, which is the ratio of the perpendicular component of the velocity in the control plane, equals with the mu alpha d plus mu alpha c in a case of a helicopter in trim, substituting 12 into 11 and recalling the trim of the helicopter here, it gives us one equation where we have two unknowns, theta 0 and theta c. Then we go to the equation which gives us the longitudinal cyclic pitch, the longitudinal disk tilt angle. The longitudinal cyclic pitch equals in trim with the longitudinal disk tilt, and we have derived the formula for the longitudinal disk tilt. In this equation we have again two unknowns, theta 0 and theta c. Now solving also this equation is with these two unknowns. Taking these two equations, we will have the trim solution for the helicopter. We can represent the helicopter control trim for a certain helicopter as a function of the advanced velocity. Here is an example for the BO105 in trim. You see this, the longitudinal and the collective, but you see also the lateral and the tail rotor collective. Now, first concerning the collective angle of the blades. As the velocity is increasing, you see that we need more collective in hover. Then as we are flying faster, we need less collective, and then we have to increase the collective. This curve is following the power curve, and it has a bucket shape. You see that there is a difference between the continuous line, which is an theoretical model, and the points which corresponds to the flight tests. This is probably due to the inaccuracies in the theoretical modeling and to the twist taken in this model. For the longitudinal cyclic pitch, actually, if we are increasing the velocity, we need more longitudinal cyclic. So we need to move forward the stick and increase the collective and go nose down with the helicopter. You see also the lateral cyclic. For the lateral cyclic, it means that we start with a very low cyclic in hover, and we have to increase the lateral cyclic and then decrease it a bit. You see a big difference between the theoretical model and the flight test data. This is due to the fact that the theoretical model considered a constant inflow. And this is a typical way of a helicopter. The trim, predicting the lateral trim needed, lateral cyclic trim needed at a low speed, it is quite challenging. For the tail rotor collective, it means that if we increase the speed, we need more pedals to correct the yawing of the helicopter. You see that there is a big difference between the high speeds as we predict from theoretical model and from the flight tests. Like this, you will be asked to represent the collective and the cyclic pitch that you will need as a function of the forward velocity for an helicopter example that you will build the simulation model. I now continue with performing a maneuver. Now, imagine that in a simulation model that we have built, we consider that we have a disturbance from hover that we introduce between 0.5 and 1 second of the flight. And that is, in a cyclic pitch, we give 1 degrees of cyclic pitch between this time. You will see that if you represent the simulation model in time, that we will have an increasing in the horizontal velocity and in a pitch attitude. So actually the helicopter, it is unstable if we disturb it from hover. We will learn that this is actually typical to the phugoid instability. What happens with a helicopter in hover? So, assume the helicopter in hovering flight when suddenly a gust makes its nose down slightly. If the pilot will do nothing, due to disturbance the helicopter will build up an attitude. As soon as the forward velocity will increase and will go nose down the helicopter, the rotor will blow back, as we learned that the flapping is always damping the fuselage motion. Then the attitude of the helicopter will decrease, but actually the fuselage will want to sway back. Now, at the end, the helicopter will have a larger attitude than in the beginning, and the rotor will want again to damp the motion and will tend to blow forward, and so on. In this way, the helicopter will become more and more unstable. We will learn next how to try to stabilize this kind of helicopter motions in the simulation model that we have built. I end this lecture of today on the helicopter trimming and maneuvering.